Hello viewers, here is Dr. Mala Das Sharma. Welcome you to my video number 129 of my channel MALACHEMPHILIC. Video number 129 is the 68th episode of Chemical Thermodynamics, where the topic is thermodynamic criteria of non-ideal solution. So let's start. Non-ideal solution. The first point is non-ideal solution, they don't obey Raoult's law over the entire range of concentration and temperature, then it is non-ideal solution. In my last video, I have discussed about this ideal solution, where you have seen ideal solution means they obey Raoult's law at all concentration and temperature. Next criteria. Unlike this ideal solution, in case of non-ideal solution, solute-solvent interactions are different from solvent-solvent or solute-solute interaction. The vapor pressure of such solution are either higher or lower than that of predicted by Raoult's law. So, the partial vapor pressure of the component A is not is equal to this mole fraction of the component A in the solution multiplied by the vapor pressure of the component in the pure state at the same temperature. Similarly, that means Raoult's law. Similarly, partial vapor pressure of the component B also not is equal to P naught B into XP. So, if the vapor pressure is higher, then the solution shows the positive deviation from ideal behavior. If it is lower, then it shows the negative deviation from ideal behavior or Raoult's law. Now, for non-ideal solution, the volume of mixing is not is equal to 0. That means when the non-ideal solutions are prepared by mixing the liquid component, the total volume will be either there will be slight increase in the volume or decrease in the volume. Then, in case of preparation of non-ideal solution, delta H mixing is not is equal to 0. That means either heat is evolved or heat is absorbed. Then, this chemical potential of the non-ideal of the component in the non-ideal solution is given by, say, mu I, chemical potential of the ith component is equal to mu I star, chemical potential of the component in the standard state, plus RT ln AI, where AI is the activity or effective concentration or effective mole fraction. For ideal solution, it is mu I is equal to mu I star plus RT ln XI, that is actual mole fraction, but here it is effective mole fraction. So AI is the effective concentration or mole fraction. Now coming to the category, first category, that is non-ideal solution showing positive deviation from Raoult's. In case of positive deviation from Raoult's law, the solute-solvent interactions are weaker than the interaction between solvent-solvent or solute-solute. That means intermolecular forces of attraction between AB molecule or solute-solvent molecules are weaker than those between the AA molecule or BB molecule. That means solvent-solvent or solute-solute molecule. So, in such solutions, as the intermolecular forces of attractions are weaker, the component A or B will easily escape into the vapor state than that of the compared to that of their pure state. Okay, and therefore more amount of vapor is formed, and this will increase the vapor pressure. So this is ideal mixing, but for positive deviation, more number of component molecules are in the vapor phase, so vapor pressure or partial vapor pressure increases. Therefore, partial vapor pressure of the component, solvent component, is greater than that of given by Raoult's law. Similarly, partial vapor pressure of B is also greater than that of given by Raoult's law. Now, this activity or effective mole fraction of such solution are greater than that of the actual mole fraction or actual concentration. So for already I told you, for non-ideal solution, chemical potential is given by this equation. For ideal solution, here it is Xi, but non-ideal solution, here it is activity Ai. But in such case or in such type of solution, activity is greater than actual mole fraction. So, due to weaker interaction, this component prefers to go to the vapor phase. okay, and causing the higher vapor pressure than expected. Already I told you. Thus, the solution behaves as if there is more of the component than the actual mole fraction indicates. The solution behaves like that, that is more of the component is present. That means effective concentrations are more. Then, for such solution which shows the positive deviation, delta H mixing greater than 0, that means heat is absorbed or endothermic. Why? In the pure solvent molecules, some intermolecular forces of attractions are there. Similarly, solid molecules also intermolecular forces of attractions are there. When solute and solvent are mixed up, intermolecular forces of attraction between the solvent and solutes are broken and solute molecules enter into the solvent molecule. As this attraction between the solvent was more than solute-solvent, that means more energy is required to break the solvent-solvent interaction and less energy is evolved when the solute-solvent interactions are developed because it is a weaker interaction. So net result is extra amount of heat is required, so heat is absorbed or endothermic. Now here delta V mixing, that is volume of mixing, is greater than 0. That means there will be slight increase in the volume. What does it mean? The total volume of such solution is greater than that of the sum of the volume of the component liquid. The reason is same, because intermolecular interaction or intermolecular force of attraction between the solute-solvent molecules are less or weaker. So compared to solvent-solvent or solute-solute, the solute-solvent molecules in the solution little bit away from each other because of weaker interaction. So there will be slight increase in the volume. Now coming to the vapor pressure composition curve. Here, this dotted line indicates the partial vapor pressure of this component 1. Okay, and for such type of solution, partial vapor pressure of the component 1, but the actual, if it behaves ideally, but actual vapor pressure of the component 1 is this one, little higher. Similarly, this dotted line indicates the partial vapor pressure of this component 2 if it behaves ideally, but actual partial vapor pressure is little more. And this dotted line indicates the vapor pressure on the solution, but if it behaves ideally, but actually the vapor pressure is higher than that. This line as per Raoult's law, and this curve is not obeying Raoult's law. So total vapor pressure is greater than as given by Raoult's law. Now coming to the examples, this mixture of ethanol and acetone. In ethanol molecules, apart from the intermolecular forces, these molecules are attached with each other associated by strong intermolecular hydrogen bonding. Okay, and when this acetone is added to alcohol, then acetone molecules goes between the alcohol molecules. Therefore, what happened? This intermolecular hydrogen bonding in ethanol molecules are broken. So what is the result? In pure ethanol, molecules are hydrogen bonded. On adding acetone, its molecule get in between the host molecules and break some of the hydrogen bonds between them. The attractive forces between the alcohol molecules become weak. Thus, because hydrogen bonds are broken, thus escaping tendency of the alcohol and acetone molecules from the solution increases. So the vapor pressure of the solution more than that of expected for an ideal solution. Now this is another example. This is carbon disulfide and acetone. In pure carbon disulfide, these molecules are having the dipolar interaction. This delta positive carbon and delta negative sulfur, they are interacted by dipole-dipole interaction. Similarly, in acetone also dipolar interactions are there. But when this carbon disulfide and acetone are mixed up, then dipolar interactions are developed between this molecule and acetone molecule, which is weaker than that of this carbon disulfide molecule dipolar interaction and acetone dipolar interaction. So, the solution is formed by carbon disulfide to acetone. The dipolar interaction between solute-solvent molecules are weaker than the respective interaction among the solute-solute, acetone-acetone or solvent-solvent molecule. That is carbon disulfide. So, it shows the positive deviation. Other examples are this water, methanol, water, ethanol, carbon tetrachloride, toluene, carbon tetrachloride, chloroform, acetone, benzene, carbon tetrachloride, methanol, cyclohexane, methanol. Now, coming to the second category, that is non-ideal solution showing negative deviation from ideal behavior. In such solution, intermolecular force of attraction between solute-solvent are stronger than that of solvent-solvent and solute-solute molecules, whereby because of the stronger interaction, they have less tendency to pass into the vapor phase than that of the pure solvent or solute molecules. Say this is ideal behavior, this is negative deviation. Molecules have stronger interaction, so solute and solvent molecule have less tendency to go to the vapor phase than that of the when they are in the pure state. So, the partial vapor pressure of the component will be less than that of given by Raoult's law. Now, for solution showing negative deviation from Raoult's law, for such type of solution, delta H mixing is less than 0. That means, during the solution preparation, heat is evolved or it is exothermic, because energy is released during this process. Why? Because initially the solvent-solvent interaction and solute-solute interactions are weaker compared to solute-solvent interaction, which is developed after solution preparation. So, less energy is required to break the intermolecular force of attraction between solvent-solvent or solute-solute, but more energy is evolved when the solute-solvent interactions are developed in the solution. So, heat is evolved, so it is exothermic. Now, for such type of solution, delta V mixing is negative or less than 0. Reason is same. As the solute-solvent interactions are solute-solvent interactions are more. That means molecules are held together more tightly, solute and solvent molecules. So, they will come little closer to each other and therefore total volume decreases little bit. That means the total volume will be less than that of the sum of the volume of the component liquids. Now, this activity or mole effective mole fraction of such solution is less than actual concentration. See here chemical potential of the component of such solution, which is given by chemical potential in the standard state plus RT ln activity. Here the activity is less than actual mole fraction. So, due to stronger interaction, the component prefers to remain in the solution, causing lower vapor pressure than expected. Thus, the solution behaves as if there is less number of components than the actual mole fraction indicates. So, effective concentration is less than that of the actual concentration. Now, so due to decrease in the escaping tendency because of the stronger interactions, the molecules of each component between the molecules, the total vapor pressure of the solution is less than that of the corresponding vapor pressure of an ideal solution, resulting the negative deviation. So, if we see the vapor pressure composition curve, see this dotted line indicates this one indicates the partial vapor pressure of this component 1 if it behaves ideally, but actually partial vapor pressure is little less than that for such type of solution. Similarly, This dotted line indicates the partial vapor pressure of the component 2 in this solution of different composition if it behaves ideally, but actually this partial vapor pressure is less than that of this one. And this line indicates the total vapor pressure on the solution if it behaves ideally, but actually for such solution total vapor pressure will be less than that of given by Raoult's law. So total vapor pressure will be less than the partial vapor pressure of component A given by Raoult's law plus partial vapor pressure of component B given by Raoult's law. Now examples here say that first example is the mixture of phenol and aniline. In the mixture of phenol and aniline, what happened? The strong intermolecular hydrogen bonding developed between this hydrogen of phenolic hydrogen and the lone pair of electron of nitrogen of the aniline molecule. Okay. And this interaction is stronger than the respective intermolecular hydrogen bonding between the phenol-phenol molecules and aniline-aniline molecules. So, strong intermolecular interaction developed here. So, this is the example of non-ideal solution showing negative deviation. Now, another example is mixture of chloroform and acetone. Here also strong interaction developed. Why? Because this chloroform and acetone, they are associated by intermolecular hydrogen bonding. So stronger interaction develops, so they show the negative deviation. And the other examples of this type are acetone plus aniline, methanol plus acetic acid, water plus nitric acid, chloroform diethyl ether, water hydrochloric acid, acetic acid, pyridine, chloroform and benzene. So this is all about this non-ideal solution. Two types of non-ideal solution. Non-ideal solution showing positive deviation from ideal behavior and showing negative deviation from ideal behavior. Thank you.